we are going to take a look at an arithmetic sequence, which we saw earlier is similar to a linear function. If we have the arithmetic sequence -3, 4, and 11, I'd like to predict the next two terms, predict or determine another term, and do some representing of the sequence. Here's a good time to pause the video, take a look at as many of the questions as you can try, and then come back in a few moments and see what I've come up with. So far, I've come up with the values for A4, A5, and A10. So I noticed that there seemed to be very little to play with, but there was a common difference, I guess, that from -3 to 4, from 4 to 11, I was adding 7. So I just continued that pattern, which is really what sequences are all about. And I was able to do that 2 more times to get 18 and 25. But then I thought about making a table of values and trying to connect the n and the an to a linear function. And what I was really exploring here was that I had a common difference for y given a common difference for x. And so that's nothing more than delta y over delta x, which of course is slope. So since delta y over delta x was constant, I had a constant slope and I had a linear function. So I wrote y equals mx plus b, and I knew that my slope was 7 over 1. And then I needed to find out the y value when x was equal to 0, so I just went backwards one step, and I found the common difference from 0 to 1 is 1. The common difference, if I backtracked, I subtracted 7 from -3, which gave me -10. And so then I checked my values of n equal to 4 and n equals 5 into my new function, and I found that I got 18 and 25. So I didn't really need to come up with any new formula or memorize anything because it's directly related to things I've already seen. So if I were to plot this sequence actually, I can take a look at both the sequence of values, and I had 1, 2, 3, 4, 5, for example, and I had -3, then 4, then 11, 18, and 25. And my linear equation would then give me y equals 7x minus 10. So if I zoom out a little bit, I can see some of those values occurring here. Maybe zoom in a little bit just so I can see a bit more. And sure enough, the linear function passes through the points from the sequence. But then I wanted to find out the value when I had 10 for the n, and it's going to be a little bit hard unless I express this in terms of the sequence, 7x1 minus 10, and I got the same value of 60. So I feel fairly confident in my approach, and I want to represent the sequence verbally, numerically, graphically, and then algebraically. Well, I've come up with my algebraic expression, my rule, my formula. I've come up with a table numerically. I've done it graphically, and now I can say that verbally this is the sequence that starts at -3 and has a common difference of 7. So now I want to generalize this result and see for any general arithmetic sequence that starts at some starting value and has some common difference, what would that formula or algebra look like? It says to start the first term of the sequence a0, I think I'm going to simplify it and just call it a, and the common difference is going to be called d. So to generalize the arithmetic sequence for an initial value of a and a common difference of d, we continually add d to each previous term in the sequence. And then we start to recognize the pattern that we have added d a certain number of times that is related to the input variable n. We can see that if n is 1, we add d 0 times. When n is 2, we add d 1 time. When n is 3, we add d 2 times, and so on it goes. So our general term for an after n terms is going to be a plus n minus 1 times d. And so if we were to plot some of these values, we remember, that these output values and the input values, the sequence values, lie on a line. So that line has a form of y equals mx plus b. And we can connect that to the linear function by finding the slope and the y-intercept. So we can rearrange this y equals mx plus b to be y final equals y initial plus mx, which is just an extension or a rearrangement of the definition of delta, the change in one variable. We know that delta y is equal to y final minus y initial. And so we have the arithmetic sequence formula. The nth term is going to be a plus n minus 1 times d. And if we rearrange this, realizing that an is like y and n is like x, we get the rearrangement that an, after we expand it and rearrange it, is equal to d times n plus a minus d. And we recognize the connection here that an is like y and that n is like x, and therefore we have that the common difference is like the slope and the value a minus d is like the y-intercept. So there you have a memorized formula related to something well known and familiar, the equation of a line. Okay, we're going to do a similar thing for geometric sequence, where we saw that in a geometric sequence the variable was in the exponent, much like an exponential function. So given the geometric sequence, find the next two terms, determine a10, and do the same steps, but this time with a different sequence. What we recognize in the geometric sequence is the pattern gives us to go from 3 to 6, and then to go from 6 to 12, there's one thing that we keep doing. We might first try 6 minus 3, which gives us 3, but we know that 12 minus 6 is not also 3, so we have to look for a different pattern. It shouldn't take very long to realize that we are going to multiply by 2, and we can generate the next two terms. So you do a similar technique as what we did in number 13, and see what happens. I'll pause the video and catch up with you in a minute. So here are the conclusions for this question. We see that A4 is 24 after doubling 12, and doubling again gives us 48. Representing in a table of values is a little bit different from how we represent sequences, because we don't need to see the 1, 2, 3, 4, 5, but it helps us to connect it to ways we've already been working, so why not take advantage of that? When we do that, we can represent more than just the 1, 2 integer values, and we can make a continuous function. We realize that this is going to become exponential growth because we have a repeated base, and so we have a base raised to a variable exponent, and so we are going to start off with the model y equals a times b to the x plus c. But it's pretty likely that we are going to take a left-end horizontal asymptote of y equal to 0 on the x-axis and choose c equal to 0. That means that we need 2 points to solve for a and b, the two parameters, and I've chosen the first 2 points, 1, 3 and 2, 6. Going through a similar process to earlier, we see that we have a base value of 2. Back substituting gives us the initial value, or the y-intercept if you will here, of 0, 3 over 2. And so we have our exponential model for the continuous variable x. Representing that as the discrete model, y is an and x is n, and then we get the exponential model in terms of n, which we can then substitute with the value for n, the specific value of 10 that we wanted. We can reduce the 2's and get 1,536. You can plot this also on Desmos and confirm, but in order just to tidy up, we'll just move ahead with part D, which is to write the general rule. And so doing that, we recognize that yet again, the general way is a rule that might not be connected to what we've seen from exponential functions. We see that we have a common ratio of multiplying by r. A ratio, of course, is gotten from taking one term divided by the previous. So if we keep multiplying by r going forwards, which is consistent with dividing by r going backwards, we get this sequence of terms successively multiplying by the common ratio of r. Now, depending on whether r is more than 1 or less than 1 in magnitude, we get growth or we get decay. And of course, if r is equal to 1, we would get a constant function. Meanwhile, if r is equal to -1, we would get an alternating function, or sequence of terms. And so we know that an, or some function of n, is going to start off with a and repeatedly multiply by r. The question is, how many times are we multiplying by r? Well, to get the first term, we don't multiply by r at all. To get the second term, we multiply by r 1 time. And to get the third term, we multiply by r 2 times. And so there's this expression of r being raised to the exponent n minus 1 to indicate that we are doing the multiplication of r 1 less time than the value of n that we are on, keeping in mind that n is 1, 2, 3, 4, like this. So it's worth talking about what happens in these special cases. If r is equal to 1, our sequence turns out to be a constant sequence of just a. If r is equal to -1, we have the magnitudes of the terms are the same, but they alternate in sign, and so we have an alternating sequence. And if r is somewhere between 0 and 1, we can see that the terms are going to decay. And we would have a decay graph that looks like this with a horizontal asymptote of y equal to 0. And if r is contained from 1 to infinity, we would have an exponential growth graph. I'll just indicate here we have growth. And the graph would look like this, and then the terms would grow to infinity. So we would see convergence or divergence depending on the end behavior. We also have all of these other negative values that we can have for a sequence in the base, but we're not allowed to have negative values for a continuous function. We wouldn't be able to draw these exponential graphs if the base is negative, but we could still consider what's happening to the convergence or the divergence of the of the sequence if the base, the value of r, is some other negative number other than 1. We can also consider what's happening with r equals 0 and other r negative values. So there are things to consider when we generalize the result of a geometric sequence. Stay tuned for upcoming videos where we find out the dramatic results about what happens if the r values are 0, negative, and so on, to the convergence of the geometric sequence, and we'll come up with some other important basic properties of sequences. Thanks for tuning in to Raylene Math.